We start with chapter number 15, Chemical Equilibrium, Unit 2. Now, under Unit 2, we will be studying or learning how to calculate equilibrium constant. Then, what are the approximate techniques that you have in order to calculate equilibrium concentrations? And then, should the equilibrium concentrations be a bit high, then how do we use the quadratic equation solutions to determine equilibrium concentrations when given K, the equilibrium constant? At the same time, towards the end of this particular unit, you will still find some self-study questions. I suggest you solve them so that you can understand how to proceed on and ensure that you have learned the concepts that are there. Again, in this particular unit, you will be setting up an ICE table and then performing all the calculations so that you understand it is a repeat of what you have done. And so with that, I'm going to start the equilibrium constant. So finish the first slide and here. So we have to write the equilibrium concentrations for K, from K, given that the hydrogen gas plus iodine gas gives you 2 HI gas. Moles of each of the components are given and they're kept in a 1 liter flask. What are the equilibrium concentration of all the species that are there? Kc is given as 55.3. Looking at this particular reaction, we see that the initial concentration of HI is 1 and I2 is 1 and the product is 0. One thing I want to let you know is always look at the volume of the flask. In this case, it's a 1 liter flask, and so 1 mole divided by 1 liter, the molarity or the concentration remains the same. So you have the change in concentration will be as the chemical reaction shows there is 1 mole of hydrogen, 1 mole of iodine, and 2 moles of HI. And so the change in concentration will be minus X for the reactants and plus 2X for the product. That is then. Then we substitute, first write the equilibrium constant equation, HI squared divided by H2 times I2 concentrations, and then substitute those concentrations. Now, in this case, we see that the left-hand equation 2x squared over 1 minus x times 1 minus x is actually 1 minus x the whole square. And therefore, we can write, if you take out the square root for this particular expression, we can solve for x as it is indicated and as shown in the solution set. Now, once you get the concentration value for X, then whatever the initial concentration is, you subtract minus X from that for hydrogen and iodine and multiply the same concentration by 2 to get the concentration of HI. A similar type of reaction is shown. And again, this you can solve it by yourself for the reaction of decomposition of dinitrogen tetroxide to give nitrogen dioxide. Now, next we talk about approximations in equilibrium concentration. What happens when the change in concentration for a reaction is much less than the initial concentration of the reactants? It turns out that when we multiply K times 100. If it is less than the initial concentration, then the quadratic equation is not required to get the answer. So always check this assumption before you continue to calculate. Now, the same example for N2 over here, we are going to double the volume and then see how to do the solution. Now, when the solution initial concentration of N2O4 is increased or to 1, then we have to use the quadratic equation. And over here, the equilibrium concentration X is given as minus B plus minus square root of B squared minus 4AC over 2A. That is the solution for the X, which we consider as the change in concentration. Always remembering that the negative values are not to be considered when solving, when you get the answer to state the equilibrium concentration. So when we put it in, the solution is there, substitute in the K equation, and you can get what the concentrations are, and then do it. So we have 2, the negative value is not reasonable, and so you can get the value that is there. It's the same equation. And again, this is to make it easy. If you're calculating concentrations from K, then it becomes very easy. Just, you know that you have the product and the reactant. And if the system is in equilibrium, then knowing the concentration, you can find out the answer, because NO2 concentration is given, K is given, and so you can calculate it from there. Now, calculating concentrations, when they write the balance equation, calculate Q, tabulate the initial concentration, known equilibrium concentrations, calculate Q concentration using reaction stoichiometry. Self-study. So this is a self-study problem. Do that. Another self-study problem to put in, so as to understand. There's a third one that is there. The last one is when calculating equilibrium concentrations, all generally they involve ice tables, and then it is easy to solve with ice tables, and it tells you exactly what to do. If K is very large, much greater than 1, then we have to use the quadratic equation. When it is very small, we can neglect it, as long as K times 100 is less than the initial concentration. That is there. Finding equilibrium constant, always, like I said before, find the molar volume of the container, and then you can find the equilibrium concentration that is there. And so we have 2H2S breaking down to give you 2 hydrogen gas plus S2. And the Kc for this equation is 1.67 times 10 raised to minus 7. First, find out the initial molarity by dividing the moles of H2S by 0.50 liter, and see whether if you multiply 1.67 times 10 raised to minus 7 times 100, whether you get less than or greater than the initial concentration. If it is far less than the initial concentration, you can straight away neglect the H2S concentration or put it as whatever the original value is and then solve. You can set up the ice table and then check your approximation, which should be within 5%. That is, the value of X should be within 5%. And so you can calculate it. And then go to the next slide. So it is very important to recollect what steps have to be used, and it is repeated in the slide again and again how you do it, so that you don't forget it. And then again, go to the self-study questions, and we come to manipulating equilibria and disturbing the equilibrium systems. This is the unit number 3. And here, these are the principal concepts that we are going to do. What are the various expressions, reverse expressions, net expressions for a series of equilibria, Le Chatelier's principle, and disturbing a system in equilibrium. So this slide is very short, but it is intense in that you have to do some mathematical problems, setups.